Hello everyone, welcome to the Department of Astronomy at IAG-USP. Thank you all for participating of this seminar. Today we welcome Dr. Patricia da Silva, researcher at IAG and currently working on Paris Observatory in France. For those who don't know Patricia, she got her bachelor's degree in physics from USP in 2013, master and PhD in astronomy from IAG-USP, defending her thesis in 2020. And since then, she has been working as postdoc researcher at IAG and now at the Paris Observatory. Patricia is interested in studying AGN and non-active galactic nuclei. She uses 3D spectroscopy analysis techniques such as PCA tomography, spectral synthesis, emission line ratios, and imaging. Patricia, thank you for accepting our invitation. Today, Patricia is going to present the talk, Nuclei of the Milky Way, Morphological Twins, the Diving 3D Survey. Questions can be addressed to Patricia after her presentation, and if you're following our seminar via YouTube, you can also send your question using the chat. Patricia, please feel free to start.
Thank you so much for the introduction and for the invitation to present my work. So I'm going to share my screen. Okay, I hope you guys are seeing it. So my work that I'm going to present here, it's about galaxies that have the same morphological type as the Milky Way. Here's this type, SABbc and SBbc galaxies. They are spiral galaxies with good developed arms and nuclear bar. And you guys seeing here, this is the whole sample of 15 galaxies. And if you guys take a closer look to this image, you probably will see a small square in the center of those galaxies. And this is the field of view that I'm dealing with. It's a very, very small portion of the nucleus of the galaxies and scales of about 300 parsecs. So the goal of this project is to determine the nature of ionization in the nuclear region, identify the main structure of emission in the nuclear region and how they behave and coexist, determine the story of star formation in the nucleus of the galaxies, and also study the stellar kinematics. Then we want to aim to compare the results of the whole sample between them and see the main trends and differences, and also compare what we know about the Milky Way nucleus. With that, we can trace evolutionary scenarios, even based on the main features and differences that we're going to find. The data is mainly optical data cubes, but I also complement with other data from different wavelengths that I'm going to talk later. So what we aim to find, what we're going to find in the nucleus of galaxies. It is believed that most of massive galaxies, if not all, have a supermassive black hole in the nucleus. And the supermassive black hole can be accreting matter to a certain rate that will be emit in such a way that we consider to be AGN. The case of the Milky Way galaxy, the nucleus of our galaxy is considered not to be active. That doesn't mean that the supermassive black hole is not accreting matter, but it means that it's not accreting enough to become to emit in a certain luminosity to become an AGN. There are many classifications for AGNs, but I'm gonna use only two in this study, which is regarding to ionization degree, which are saffers with high ionization and low ionization nuclear emission line regions that can be AGNs with lower ionization. Why did I say they can be? Because liners can also be post-HB stars. they kind of fake the linear emission. So how we discriminate liners from AGNs or stars? Well, as I said, the AGN emission is very particular and emits in certain emission line ranges that only AGNs can emit, or emits certain emission lines that can only be found in AGNs, as neonium 5, for example, or even, which is the thing that I'm using in my work, hard X-rays. So if I find a compact hard X-ray sources where when I'm seeing liner, the line is an AGN. As you see in this image, there is one example of feedback of the AGN, which is the radio jet, that can also cause another feedback such as outflows. They are related. And this can interfere in the star formation of the circumnuclear regions and causing the star formation or even quenching star formation. And the galaxy can interfere in the nuclear region by feeding gas towards the nuclear region and making the AGN even more powerful and causing more feedback. So there is an interplay between galaxy and AGN that co-evolve together. So how I'm going to see the nuclei of those galaxies? Well, we use data from the Diving 3D survey, which is the Deep IFS View of Nuclei of Galaxy. It is a survey that has a goal of observing galaxies in the southern hemisphere with a B band magnitude less than 12 and galactic latitude greater than 15 degrees. The survey comprises 117 galaxies in total, and the data is optical data cubes obtained with mostly Gemini multi-object spectrograph from Gemini South telescope. But we also have Gemini North and also data from solar integral field spectrograph sits at the solar telescope. The goals of the Diving 3D survey are pretty similar to the goal of the Milky Way morphological twins project. They aim to study the nuclear and supernuclear emission, the gas, the stellar kinematics, and also the stellar emission in order to have more robust statistics, because we are not only talking about one specific morphological type of galaxy, but many other galaxies with different morphological types and different distance. So we want to have a robust statistic of the main phenomenon on the nuclei of galaxy with high resolution data, with high spatial, 0.6 arcsecond, and spectral resolution, 1.3 angstroms. That was never done before. So here I'm citing two papers, Menezes et al. 2022, which is a paper about a smaller sample, is a mini Diving 3D, it's called, a small sample of the Diving 3D, which has preliminary results. And also, I'm also citing the paper of Thiago Ricci et al. 2023, which is about the elliptical galaxies of the Diving 3D survey. So I invite you guys to read that. So I'm talking about data cubes. So what is a data cube? It's an astronomical data set with two spatial dimensions and one spectral dimension. In other words, it's an image on which each spatial pixel represents a spectrum. Or you can even say that you have a spectrum that each spectral pixel represents an image of that emission. So how do we get data cubes? We get the data from the telescope and do the data reduction. In the case of the Gemini telescopes, we use the Gemini packages in Iris. And in the case of solar, Python scripts. The data treatment, I don't have time to talk in detail, but here are the three papers that describe very well all the data treatment that we do. And with this data treatment, we can enhance a lot of the quality of the data cubes, and we can get even more information than people who don't treat the data cube accordingly. For the data analysis, I use some tools. So I use optical emission line ratios to determine the emission nature of the sources that I'm looking at. I use images of emission lines to see the morphology of the gas and how they are disposed in the field of view. I also use channel maps and velocity maps of the emission lines to see the gas kinematics. And I use spectral synthesis for many reasons. The first one is to remove the stellar emission from the data cube to study all the gas analysis. And I use also spectral synthesis to identify the stars doing the starlight by doing the starlight software. I will get then stellar populations by age and metallicity, and I do the penalized pixel fitting that is optimized for the stellar kinematics. As I mentioned, I also include analysis for the instruments and wavelengths. So I use Hubble Space Telescope because the images are have a higher resolution, spatial resolution, and sometimes it's good to see in detail the nuclear region, and also because they have greater field of view. So it is interesting to see the Hubble Space Telescope images superposed to the GMOS images to see the main structures of the galaxy and how it connects to the nuclear region. I also use symphony data that is in the near infrared to study the molecular gas and emission without so much interference, of dust. I use also Chandra data, as I mentioned, to see the hard X-ray emission, but also to study the soft X-ray emission. But I just do like qualitative analysis just to see the morphology and how it's exposed those, if there is emission and how it is exposed on the field of view. And I use MUSE data, which is also optical data cubes. But in this case, MUSE have a way much bigger field of view. And I use MUSE, for example, when I have a circumnuclear ring that is cut on the field of view of GMOS, and we don't see the whole circumnuclear ring. So I get the MUSE data cut around the circumnuclear ring to have the whole, to make the study of the whole structure of the nuclear region. And finally, I use ALMA data to study, that is in radio, to study molecular gas emission and kinematics. So in this slide, I'm showing a very, very, very brief summary of actually the main things that I'm going to discuss compare with the Milky Way nucleus. So this image is very interesting because it shows that the Milky Way show the 50 parsecs of the Milky Way nucleus. It shows that the Milky Way nucleus has many structures, is very rich. It has many H regions, star forming regions, and clusters, and there is X-ray emissions, etc. So Sagittarius A star, it is located here in Sagittarius A, and is a compact radio source that contains a supermassive black hole. Everyone knows this image. That is the shadow of, that was taken with the Vector Rise telescope. And it has the most precise black hole mass ever calculated. We have also the two clusters that are very interesting, that are the Arch clusters and the quintuples. They are interesting because they have a considerable quantity of Wolf-Rayet stars. And Wolf-Rayet stars are interesting because they are massive stars that are expelling winds of the shell with high velocities. So it is easy to detect. We will detect on our set of data with our spectral resolution very easily. So the Milky Way has a lot of them, of this kind of stars in distributed on the nuclear region. So this is very interesting. Another thing about the stars on the nucleus of the Milky Way is that although it has a lot of young stars, the majority of the stars on the bulge of the Milky Way can be represented by very old stars, 11 billion years, with high metallicity. So I want you guys to hold these three informations that I'm going to compare with the results that I'm going to show now. So as I mentioned, also there is a supermassive black hole and it is accreting, but is not accreting in a high rate to be considered active. And actually, there is a study that says that if an extragalactic observer will look into the nuclei of the Milky Way, they would, the nucleus of the Milky Way, he would see that they will classify as an A2 region, which is a non-active nucleus because of the star formation is the main source of emission. Okay, so now I'm going to show the results of my work. The first one is quite surprising, actually. So, as I mentioned, the Milky Way is not considered to be active, but its counterparts are actually, the majority of them lies in the AGN part of the diagnostic diagram. So how do we put these points here? We extract the spectra on the size of the PSF on the central source of the field of view. Each one of these galaxies has a data cube, and the center of the data cube has a source. And this is the nuclear source. And then we take we select the spectra, the size of the PSF point spectral function, and we calculate the emission line ratios and plot in this diagnostic diagram. So we are seeing here that most of these points, the color points, which are the Milky Way morphological twins, lies in the part of the AGN of the diagnostic diagram. Okay. This is interesting because in the Palomar survey, which is a survey that is actually the diving 3D survey was inspired by the Palomar survey. It is a survey very similar to the diving 3D. It was also limited by magnitude. The Palomar survey has is not data cubes. It is actually a spectra extracted by a large area. Actually, this area is quite similar to the whole field of view of the diving 3D, depending on the distance of the galaxy. Let's say is more or less this. So they have this slit. They take the spectra. Is only one spectra to this whole square that englobes not only the nuclear source, but the circumnuclear sources. And we can see here in the diagnostic diagram that the Palomar points distribution, there are the gray points here, they have a quite opposite distribution compared to the points of the diving 3D survey. So why does that? Why there is this difference? Well, if you look at the circumnuclear regions, which is something very important in these galaxies, I don't know, I have to compare with the other galaxies of the survey, but these galaxies of this morphological type, all of them have at least one nearby region that would be a narrow line region, or more frequently, H regions around the nuclear source, at least one. And we see that the distribution of the circumnuclear emission, it is quite similar. And if you see here, the percentages are quite similar um, to the Palomar survey. So what does that mean, all of this? It means that the circumnuclear emission cannot be ignored. You have to take into account that if, for example, you have a low luminosity AGN and a very strong A2 region nearby, you take the spectra to calculate the emission line ratios of the nuclear region of the galaxy with the whole field of view that englobes the two emission, you will have a contamination of the H2 region to the nuclear source. And then you have a misclassification of something that will lie in the linear part of the diagram will fall to the transition object parts of the diagnostic diagram. We have more transition objects here in the circumnuclear emission because we are seeing H2 regions that have the contamination of their emission by the nearby AGN. Is the contrary. So when we have, as much as we have the greater spatial resolution, we will be able to separate even more the sources and have this region here, that the transition object, to be depopulated, not have much more points as we have in the past. So that's a very important thing, because when you are classifying, many surveys are classifying agents with low spatial resolution. So you are taking not only the nuclear source, you are taking everything around it. And it can be a lot of H2 regions, sometimes a ring with a lot of H2 regions, very bright, and we contaminate something that will be a liner will fall to the transition object part of the diagnostic diagram. Another interesting thing is that all of the liners here, we have the question again, it is an actually AGN or it is false AGB stars. So we had to search for Chandra data to see if there is hard X-ray emissions, and we found that the ones that had the data, 63% of the liners are confirmed AGN. So that means that most of the galaxies of the sample are active, and they spend most of the time being active, 6-7%, about 6-7% of their times of their lives being active, and the Milky Way is not. So that could mean two things: or the Milky Way was active in the past, which we have some evidence of that, and will not be active anymore, or that the Milky Way will be active in the future. So this is something that we can, one evolutionary scenario that we can think about. So moving on, regarding the gas morphology, it's very interesting to superpose different instruments and data from different instruments to see the general scenario of the nuclear region. And in this case, I did this multi-wavelength analysis on NG613, which is the most richest nucleus of the whole sample. It has everything. It has radio jet, it has ionization cone, extended soft X-ray emission, circumnuclear ring, nuclear spiral. So it's a very interesting object. And here I'm showing the example of feeding feedback on the AGN of the galaxy, which is a liner, by the way, but it has emission of neonium-5 and also compact hard X-ray emission. So in the soft X-rays in blue, we see there is extended, and the distribution of this emission is very similar to the distribution of the emission of oxygen 3 observed with SIFs. And oxygen 3 is a line of high ionization that we, based on its morphology, we can say that is the ionization cone of the AGN. So we see that there is a correspondence between the emission of the ionization cone and the soft X-ray emission that can imply that there is happening photoionization in the ionization cone is very strong. And this yellow arrow here represents the radial jet that was identified in this galaxy. And these three other arrows here represent outflows of gas. One of them was detected with H alpha from the channel map of this emission line. So we see a little bit of the rotation of the circumnuclear ring. And here you can see why we have to get a bigger field of view. We only see the inner edge of this circumnuclear ring. But we can see here a very collimated emission with high velocity points towards exactly, right, more or less the radial jet. So we have an outflow, and these other two outflows here were detected with oxygen 3 channel maps. And we can see that there is an excess of soft X-rays towards this direction of these outflows, which means that they are very powerful. Another interesting thing showing that these outflows and radial jets are so powerful that they broke this circumnuclear ring seen with ALMA, which is molecular gas. We can see that there is a break here exactly in the part of the outflowing radial jet. So the feedback of the AGN is causing a disruption on this circumnuclear ring. The interesting thing on these superpositions is actually this image, which is the subtraction of the filter F814 minus F475, which shows the red emission opposed to the more blue emission. So it shows where lies the dust, etc. So you see a very clear structure here. And this structure is actually associated with the bar of the galaxy. And we can see that this structure is connected to the ring in many points, and also to the nuclear spiral is better seen here. So, based on other studies and also the rotation of the circumnuclear ring, we know that this structure is actually feeding the nuclear region. Okay, not only the circumnuclear ring and is forming stars along as it rotates, but also on the nuclear spiral feeding the AGN. So this is a very interesting case of feeding feedback of the AGN, the interplay of the galaxy and the AGN. Here's some only examples of the gas kinematics on the same galaxy. So here you can see the rotation of the ring with the molecular gas, seeing Symphony and also in ALMA. And the channel map already said. So in the whole sample of the MWMT, only 30% of the gas present clear evidence of gas outflows. Okay, not that we don't see in many others, but it's quite difficult to interpret if it is actually an outflow or a superposition of rotations, etc. Finally, for the results, I'm showing here an example, 3 histograms actually. The histogram of the total mean the results of the stellar spectral synthesis with starlight. We can see the high metallicity stars, intermediate metallicity stars, and low metallicity. In red, we see the high metallicity. We don't see low metallicity stars in those galaxies. And here's the ages. So we can see that there are predominantly high metallicity stars and old, as is this in the Milky Way, old and high metallic stars. Okay. Another interesting thing is that between the sample of AGNs and non-active galaxies, we don't see any differences between these two histograms, any big differences. So that could mean that the AGN presence, although it can quench some star formation or cause star formation in some cases, is not making any differences overall in the nucleus of these galaxies. Or it can also mean that we don't have enough resolution on our stellar bases, etc., to see those differences. But the most interesting thing on the results regarding the stellar populations is about the Wolf-Rayet stars. We did not detect any Wolf-Rayet stars in none of the galaxies, not even in the galaxies that are non-active, which can mean that the Milky Way is actually different from its analogs. Meanwhile, the Milky Way is non-active. It has this kind of stars. It has some similarities, like the age of the stellar bulge, but their counterparts spend most of the time being active, and they don't have those stars. So it means that the Milky Way is passing through a different phase of existence, and probably we go, as I said, probably we go being active in the future. The circumnuclear emission, as I said, is very important in this galaxy. So if you are classifying the emission on those galaxies, please be careful with the spatial resolution. And as I mentioned, there's no difference in stellar archaeology between active and non-active galaxies. We don't know yet if the AGN is not influencing or not. So the future plans of this project is actually what I'm doing now. That's why I'm here in the Observatory of Paris. It's to study the molecular gas feeding into the nucleus using ALMA data with buried galaxy and non-buried galaxy. And we'll see the differences, how much the bar influences the gas to fall in the nucleus, how this happens. Another branch of the continuation of this project to compare these samples with non-buried counterparts, the SBc galaxies, to see what is the influence of the bar in the nucleus of the galaxies. Does those galaxies have much more H2 regions around the nuclear source or not? Or they are more active or not? So this is going to be interesting to see the cooperation between these morphological types. And for the diving 3D, we actually have a lot to do yet because we didn't finish yet to analyze the whole sample. It is 170 galaxies, so it has a lot of things to do yet. And if you are interested about the diving 3D survey, the projects, the papers, and if you want to get involved in diving 3D, there is always a place for you. And you can enter in the diving 3D website, and you will see more information about this project and many others. So thank you so much.
Thank you, Patricia, for the excellent talk. We will open now for questions. Here in the auditory, we have... Okay.
Hi, Patricia. Thank you for the talk. I have one question about the one galaxy you showed, the NGC 613, that you showed the morphology of the circumnuclear ring, and you said that the jet broke this ring. I would like to ask if this configuration is normal, the ring and the jet on the same plane?
We assume that it is because of the coincidence between the position angle of the jets and the place that is broken in the ring. But for sure, they are not in the same plane, but we don't know if the outflow is also behind, and is causing the gas to be expelled as well. So we assume that because they are in the same position angle, right? It's very coincidental.
Thank you. And can I make another question? So for your some of the conclusions, is that it seems the activity is not influencing so much the star formation history. Is it so I understood correctly? One of the last conclusions, there is no clear correlation.
Yeah, because the histograms between people not hearing me.
We're hearing you.
Elizabeth said that
We hear.
cannot hear. Okay, so we continue. There's no much difference between the histograms of active galaxies and non-active galaxies. So it means that, well, the AGN is not making much differences there. We would expect like if the AGN was quenches the formation, we would have like less young stellar populations in the histogram, or is making more. So we have more young stellar populations, the flux fraction, right? More flux fraction attributes to young stellar population than the others non-active, or even the metallicity. It will be different, but we don't see any like evidence difference between the two histograms. So one of the interpretations could be that the AGN doesn't make any influence on the environment regarding the stellar populations. But there is a thing. We might not have a good spectral base, stellar spectral base resolution to see the differences. So I cannot say for sure that the AGN is not making any differences. That's what I'm talking. It could be, but
Thank you.
thank you.
We have more questions. Okay, I have one question. So, I have an elementary question actually. So, can
Okay.
you please explain how the diagram, the diagnostic diagram that you showed, how it works? Can you explain, please? Because like there are some parts that the object are safer, and so are some parts that they are H2 regions and liners. Why is it that?
So let me share my screen, actually. Let me just. Okay. So the diagnostic diagram, it is built, it is a theoretical thing, built based on ionization degree levels. And these emission line ratios are very dependent on the ionization degree. Oxygen 3, as I said, is a high ionization emission line, and H beta is not. So if you have more oxygen 3 than H beta, you have a high ionization degree. So your point will come from the H region that is low ionization to high ionization, go to safer, okay? And the nitrogen over H alpha is more or less the same, but it goes to this part of the diagnostic diagram. Okay, so it's more like it is a general classification, and these lines here are theoretical. So some are theoretical, some are empirical, and they divide the
it's difficult
different.
to see it. Can you put it on presentation mode, please?
Sorry. Okay, I will put. I could feed. Okay. So there is this the divisions between sacred lines and trees and transitional objects were made theoretically and also empirically. I don't remember each one. And there's that, like, it is the dependency of the ionization degree with the emission lines. So if you have these ratios, they are sensitive to the ionization degree changes.
Okay, now I understood. Thank you very much. Now, Betty, can you make your question, please?
Okay, Patricia, very interesting results. So I have a question regarding the star formation feedback, because you have these rings that are the most obvious positive feedback of AGN passage over there. But also there is, this positive feedback also depends not only the AGN power, opening angle, activity itself, but also on the star formation rate or the star formation activity of the system itself. Of course, you are talking about systems that have active star formation. But so my question: when you have these rings, what is the distance from the nuclear region that you observe in your sample? And have you seen these rings because they are also observed in nucleus, in liners, in Seyferts? So if you have seen any difference between these different classes. And also I'd like to mention that we performed magnetohydrodynamical simulations of these star formation versus AGN feedback. And in our simulations, we do see these rings, and their size and time of activity scale is really directly related to the power, the opening angle of the AGN, and also the star formation rate of the system. So it's, this feedback is really from both sides. That's why I'm asking you, what is the morphology, general morphology, and if you see differences between these different classes of active galaxies, fleets, liners, star formation, Seyfert, starburst.
So about the scale of the rings, they are about 300 parsecs.
Right.
Yeah, the whole field of view of the. I even show the image of the H alpha channel maps. You can see only the edges of the circumnuclear ring indicate, because they are also the field of view. They are around. We have to do the SIF's observation was because we want to study the circumnuclear ring of this galaxy. So we have to get a bigger field of view.
Yeah,
so
and in the simulations, we do see that this hole, because you have the ring, and the hole is really dug by the passage of the AGN wind. So it should be there. But the scale 300 parsecs is exactly what we see. But do you distinguish? Do you see any difference between the different
types, the classifications? Well, for the rings that we could detect, they are actually liners. I don't see in Seyferts. I didn't see in the Seyferts. And there is one ring on one galaxy that it is a liner, but we don't know if it's an AGN or not. So
right.
But it's only on liners so far.
In all your sample.
Yeah.
Right. This is interesting.
I think we found like 4.
You have
galaxies that have.
You have ULIX in your sample.
No.
Okay. Because there are systems with this evidence as well. And do you have any comment? Because there was this Australian survey near in the galactic century, near the region, at the same wavelengths, more or less, molecular molecular gas do you have any synergy? I mean, does your research, your survey, have any synergy with these observations, for instance, made with the Australian telescope facility, or you were not aware of this?
I'm not. I don't know.
Okay. Yeah, I can send you more details on this because
The first paper from the Diving 3D, you can see Steiner et al. 2022. There is a comparison between the Diving 3D survey and the other survey. They are similar. Maybe it's there. Okay, you can take a look at that.
Only as a comment that, all these surveys, low energy surveys, will be very important for galactic plane surveys that will be performed in gamma rays, because the coming Cherenkov telescope array has a plan of doing an entire galactic plane survey, and the synergies with the other wavelengths are very important for this, the determination of the sources and classification. So, this is something to be aware that in the other wave, the highest energies, there will be a lot of information in this regard with the activity in these
Nice.
in the aging galaxies of all, and in our own galactic plane and in extragalactic objects as well. But this galactic plane survey will be very helpful to understand the sources and the activity around the nuclear region in our own Milky Way.
Okay, thank you
for the talk.
Thank you.
You're welcome.
Hi, Patricia. Hi, Maria. Hi. I don't know if you can see at least the back of my head.
Yeah, I see you.
Is this me? Okay. I will turn around. I'm sorry, so I can see you. Okay. I have a question related to the clusters in the Milky Way. You mentioned the quintuplet and the Archer's cluster. The first question is do you know if the quintuplet cluster is as young as the Archer's cluster? Are they the same age, or you don't know?
I don't know.
Okay, and then you mentioned that
I got the impression that they are similar.
Similar.
But, I'm not gonna risk on that.
Okay, it was just a curiosity question. But you mentioned that you detect the Wolf-Rayet stars in both, and they are forming massive stars. And I was wondering how well can you determine the members of or can you be, I don't know, 100% sure, but can you measure how many of these Wolf-Rayet stars are in each of the cluster, or it is really contaminated from of the sources that?
Well, first of all, this is not my study of the Wolf-Rayet stars detection. So,
okay.
I can share my screen again to show. The paper. So it is this paper here. Okay, you can take a look at that.
Yeah.
They determine. Okay. How well? If I could detect Wolf-Rayet stars, I will not be able to resolve them.
Okay.
So I will just detect the spectral signature of them. They are there.
I
can even show one example here of Roberto did. Let me just show it. Are you guys seeing?
Not yet.
No?
Not yet, but is now, yes. I think it's better if you put it in the presentation mode. Yeah, this is.
So you can see here the signatures of Wolf-Rayet stars on this. Let me just Okay, I will show the paper later. So you can see here, would be able, if there was Wolf-Rayet stars on the sample, we will be able to see these bumps on the calcium and helium emission lines, or even others like oxygen and nitrogen. But we don't see any. We don't see anything like that. So let me show you the paper if you guys want to see.
Yeah.
This is the paper.
Great.
Okay.
Thank you. Okay, thanks a lot.
You're welcome.
Any more questions? Okay, so let's thank again Patricia.
Thank you so much. It was an honor.
Thank you a lot. It was a very great talk. And now we will have our coffee break here outside the auditorium. So we would like to invite you to come with us and have a coffee break too.
I will have my own coffee break here.
Yes. So it's ok. Então agora a gente pode falar em português.